coworkers. So that excited me as a result of this advent of the alternative redox couples. So I decided to systematically start testing uh, you know my carbon composites and all these kind of available, both commercial and fabricated and synthesized nanoparticle based kind of carbonaceous material. And today I'm going to speak a bit about them. And before that, some of the carbonaceous counter electrodes are already reported, but not I would say concretely, but like sometimes some kind of like composites with platinum nanoparticles. And like also like some of them are only characterized with this kind of electrochemical characterization by making this symmetrical cell configuration. But no concrete study like was reported to the best of my knowledge, except one or two. So that's why like it motivated me to move and do some things like in this direction. So one of this article before my move to the new place at University of Oulu, so I tested with my coworkers a low temperature single wall carbon nanotube, screen printable paste that you can coat both on glass and also like on flexible polymers, as you can see. So it is like it was obtainable from this Brewer Science, a US company. So we tested these devices with these copper electrolytes. You can see all the details of the electrolyte composition. And like when I fabricated these devices and when we tested under both full sun and then like half sun light intensity, so you can see that very impressive, like more than 7% efficiency was achieved under full sun, the champion device, and as well as under half sun we achieved like more than like 8% kind of efficiency. So that was kind of one of the very eye-opening kind of results compared to the traditional platinum. As you can see that okay, far lower performance was achieved with the traditional platinum catalyst. And why it is happening? It is because of the poor catalytic performance in the dye sensitized solar cells, unfortunately, with these bulky redox shuttle base kind of electrolyte compositions. Either you do with the cobalt or with do the copper redox shuttle. So as you can see, the far significantly different kind of impedance response. This red semicircle corresponds to the Nyquist plot of the platinum counter electrode base dye sensitized solar cell, where you can see a fraction there in the first picture upper left, the impedance response of single wall carbon nanotubes counter electrode. And when you zoom in, so then you see like in between 4 to let's say 20 ohms the impedance response. And then like now it is established that with different characteristic frequency we see different semicircles, and I have mentioned here. So at the very lowest we observe mostly like the charge transfer resistance. However, like in the carbonaceous material we also observe like some so-called this input diffusion resistance. So and then like at low frequency we also see the charge transfer resistance. And then like at sorry, like at the very high frequency we see this input diffusion resistance, the first semicircle from the left. And then like at some low frequency we observe like the charge transfer resistance of carbonaceous counter electrode material. And then at a very low frequency range like we observe the diffusion resistance. So here like we observed through the electrochemical impedance spectroscopy that what was the reason of efficient performance of a complete solar cell having like a single wall carbon nanotube based counter electrode. And another fact that okay, because of this bulky redox couple, like they exhibit very high diffusion resistance, as you can see here. So the previous these in the previous slide, and this you know in these results, so we fabricated devices with a 10 micrometer base Surlin thermoplastic. So however, when we made the symmetrical cell with a 25 micrometer Surlin thermoplastic, so you can see a significant increase in the diffusion resistance. So that gives you an idea that okay, how you should optimize the device structure in order to extract the best performance of your devices. So these first result, again, like was a great motivation for me. In fact, although we use this single wall carbon nanotube, screen printable paste. However, like one fact I want to bring it into you notice that this paste was very expensive. I believe it would cost like for few grams like around 17 or 1800 dollars. So that is not kind of bearable when you try to look the overall cost production. So one of the motivation was to replace this to more kind of cheaper and low cost efficient alternative. So then I tested very quickly the screen printable paste from Dynamo and compared it with again like a screen printable paste of platinum for the conference at that time that was announced by Dynamo. And you can see here like we just presented through a poster presentation the impedance response of both type of catalyst material having with loaded with the copper electrolyte. So it's again like was very reproducible results where like the carbonaceous kind of composite catalyst material. You can see all the details like with this paste kind of code. But this paste of carbon, it is a low temperature screen printable paste, and that again outperformed in the electrochemical characterization compared to the screen printed platinum catalyst based counter electrodes. So then because I was like in a move to my new university, so although we have like done a very good study that after testing this previous dynamo paste, so we also, because I have been efficiently involved in the perovskite solar cells research and development activities. So some of the materials like including this carbon conductive layer paste kind of which we are producing through the pastes. So I also decided to test that. And we also like printed those counter electrodes. It is like the paste from the solaronics, and then you print like you get around thickness of like 4 to 6 micrometer. So according to that, because previous paste of carbon nanotube was just 1 micron thick, so you have to adjust like the thickness of the thermoplastic. So that's why we decided to use like the 25 micrometer thermoplastic. And as you can see here, having this kind of screen printed high temperature paste which you print and then you sinter it at 400 degree. So we again achieve very impressive performance compared to the single wall carbon nanotube based kind of counter electrode and the traditional platinum, where like the very low cost this carbon paste that was composed of carbon black and then graphite nanoparticles, it outperformed in the presence of this copper electrolyte to both like the other existing catalyst layer, and for a reason because like it provides like highly porous and then more catalytic sites. So that's why like when we did the again like the impedance spectroscopy, so that gave us a very low charge transfer resistance that influence over the fill factor and also like the open circuit voltage in the solar cell. And most importantly, as like as I mentioned, As you can see here, like, nowadays the fashion is to also like test with the low light intensities. So then you can see that even like they were giving very impressive performance. So, and at that time, few, 1 or 2 years ago, the trend of producing like the stability results with this alternative redox shuttle was not that concretely established. So we decided to soak these devices under very low stressful condition, meaning that we soak the devices under this artificial LED base lamp, like with having like a 1500 lux. And as you can see here, that the carbonaceous material like also showing very good chemical inertness, and then they did not show any degradation. So that is a very very promising result, like, if you see from the perspective of long term stability reports, like, that has been, now that have been coming up now with all these kind of alternative sets of material. So the learning is that these carbonaceous materials can be one more alternative when assembled to, let's say, this alternative copper electrolytes. And also, like, we are observing that okay, diffusion resistance can be optimized with an intelligent optimization of the thickness of the thermoplastic, and they are like very chemically compatible with this new electrolyte. And also, like, we can get very very good catalytic activity for these electrolyte. And also, like, potentially it can also be doped with this p dot catalyst, which has been mostly reported with these alternative kind of uh, electrolyte. So nevertheless, why I am interested in developing this carbonaceous counter electrode with these alternative redox uh, couple base electrolytes. As you can see here, like the present geometry of the copper electrolyte based DSSC that has been reported like in numerous publication. So at the moment they are having like few limitations, which I believe very important to address. First of all, like, it is a very thick device structure composed of two electrodes. And if you are like, aiming to integrate these kind of cells into portable electronics, so this thicker kind of device design is not suitable, because you need to produce very thin kind of uh, energy harvesting kind of component, so that it could integrate uh, you know easily like into the this portable electronics and IoTs. Secondly, as you can see here, like as I mentioned earlier, the you know you produce this solid state zombie cell by first injecting the electrolyte through the holes, and then you wait like to for the solvent to evaporate from the channel, and then you introduce it again and again. So it's a very slow process, and that cannot be kind of opted for the mass production or like the rapid production. So there should be like some alternative kind of materials or methods should be developed for this introduction of this electrolyte in the cell channel. And also, like, at the moment, as I mentioned, that because it is reported with the p dot catalyst, so under harsh conditions, like the chemical inertness of p dot catalyst has not yet established, despite of some initial kind of stability reports, because in the presence of harsh solvents, so this p dot as a conducting polymer catalyst can dissolve. There is a study appeared with a cobalt redox couple base electrolyte, where it was shown that the cells degraded under some kind of stressful condition. So the stability of the p dot catalyst has yet uh, has to be established. And so more studies are expected in near future. So, and another thing is, as I mentioned, that like this device design is mostly nowadays achieved without having any thermoplastic in between them, and by rather than by directly pressing the counter electrodes and the photoelectrode substrate, and then you seal it, as you can see here, from the edges with a UV glue, and then you introduce like the electrolyte in the cell channel. So with this kind of assembly, it is very, very difficult to the best of my understanding, to produce the traditional serially connected, or even like the parallel kind of connected large area, solar modules, to achieve like more higher voltages and like more power. So as you can see, all these cells like which are reported, you can see the single cell kind of device design. So which I believe is because of the limitation of this device design, that you are able to produce a long single cell, but it's still like to the best of my knowledge, no kind of device design based upon like serially connected or parallel connected modules has been reported. So that's why the printing, or like the printed carbonaceous counter electrodes, provide you an opportunity, so which we also summarized in one of those review article which I mentioned in my earlier slide. So we can really design based upon the printed carbonaceous counter electrode based kind of material, that instead of two electrodes geometry, like a solid state kind of device design, so you can like really produce these cells on a single substrate by first laser patterning the glass electrode to convert it to obtain the contacts for both electron and hole transportation. And then like you can grow at one side like all this electron transporting layer. Now we know that how to do it, either like by screen printing a compact layer, or like by TiCl4 treatment, or by spray pyrolysis. And then like you can print the similarly like you produce for the two electrode based kind of device design, so mesoporous titanium layer. And then you can even potentially print the die through inkjet, and also like the copper electrolyte, and then even like the inkjet printing of the p dot, and then you can screen print like either high or low temperature paste based upon the requirement. There are many flavors of both high and low temperature paste available for this carbonaceous material, even commercially. So either you can make it, or you can get it. And then like you can obtain like the silver contacts, and then you can passivate the whole device design with a printable epoxy. So this proposed design we have we recently proposed in our this review article. You can all download it. So the motivation is that can we achieve this device design? So I believe yes, as a result of some of very very uh, uh, impressive work that was reported in recent past by myself along with my coworkers. So first of all, we reported this dye sensitization process, like with the automated or semi-automated inkjet printer. So where we showed that okay, the traditional dye soaking process, it needs overnight soaking of titanium electrodes like in a dye bath, and then a monolayer you get. But like we replace this process by making like the concentrated dye solution that can be filled in the cartridges, and then like you can really sensitize, and then you can pattern even like multiple dyes on a single titanium electrode. And nowadays, like since we all know that achieving like more higher short circuit current densities is possible by co-sensitization, nevertheless, and now even like some controlled volume of both dyes have been mixed, if you see the recent reports. But previously, like it was very random, that okay, like the dipping time in the both dye solution in order to achieve the co-sensitization was random. So that's why the mass loading for individual dye was not possible to know. And even like in this kind of co-sensitization method, like which is like currently implemented, to the best of my knowledge, like you make two different solution of concentration and then you mix in a proportion volume. So but it's still like when you sensitize the dye, so then it's still like the dye loading volume of both dyes are unknown. So but the inkjet printing provides you to systematically like make a loading with a controlled volume. So that's why it could also like affect the overall process. Similarly, so then not only the dye, we also like showed like that okay, even the electrolyte can be also like successfully like printed. So this was like one of the report with the ionic liquid based kind of electrolyte with iodine and iodide triiodide redox shuttle that was successfully printed over the titanium layer. And what does it allow? It allows to produce the whole free kind of solar cells. So and then suppresses all this non-active area, as you can see on the right side of the picture, holding like with a lot of non-active area is induced as a result of drilling holes and where you have to inject the electrolyte. So that affects the overall cell resistance. So if you directly print on this titanium electrode, so all this unnecessary kind of non-active area can be significantly suppressed. And then there we showed that okay, if you minimize this non-active area, so then the performance can be improved by retarding this the overall cell resistance. So if we have the printed dye and the printed electrolyte, and also I was looking through that okay, the inkjet printing of the p dot is also like established. So then it's possible like to achieve this kind of printing strategy. And why the printing is more important is because that the term which is called reliable process control, so that is like that is immensely needed like in order to build a successful kind of nanotechnology based kind of either it is a energy system, or either like it's any kind of modern electronic system. But if you are not showing the reliable process control in it, meaning that the materials you are using, they should be kind of integrated with a controlled volume or in a reproducible fashion in order to achieve like high reproducibility. And this is like which we proved in one of the case with the perovskite cells, where uh, all these other layers of this monolithic device design of perovskite cell was done with the scalable techniques like screen printing, except for this manual infiltration of perovskite. And what was happening that the performance reproducibility was getting compromised, meaning that we were not having like this kind of reproducible efficiencies among the fabricated batches. So when we replaced this inkjet infiltration, I mean like the manual infiltration with an automated inkjet infiltration of the perovskite precursor ink. So it was like very impressive to show that okay, how we can control the the volume of that ink, and that consequently uh, you know was affecting on a controlled way of improving the photovoltaic performance. And then we got a then we started receiving very reproducible devices. So that's why if you implement like in this fabrication sequence more like this kind of scalable and kind of reproducible kind of fabrication method, so then the reliability of that system like will be increased. So this is kind of my message that for today, that we can potentially like achieve like an alternative method. I have discussed like with all the honorable my colleague professor like Professor Hackfeld, and also like I have been speaking with other colleagues, and very good response like I received. So we are trying to develop like this structure, uh, and so some very good development, as you all know, now there is a company called Exeger. So they have received like not only very impressive fundings, but also now they are able to demonstrate like the successful integration of 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 of, of this technology. And very recently, this one of the videos appeared on YouTube. You can all see it, where like the successful integration in the headphones was demonstrated, and now you don't need to charge these headsets, so they can work like under ambient conditions, lighting conditions, and some more stuff like is coming up. So this is like a very kind of impressive development, and that makes kind of that gives an indication. And another interesting fact is that because the traditional challenges of the dye sensitized solar cell were in terms of the long-term stability, one of the biggest challenge was how to keep the liquid electrolyte inside the like the cell channel. But deputing them under ambient light conditions and indoor conditions like gives you and a possibility to even like use this kind of low viscosity cell solvent, because mostly these cells will not face like the harsh conditions, like if you were targeting, and if we target to deploy these cells like under the harsh climatic conditions. So the lifetime can be impressively achieved. So that makes the belief like that okay, this technology can be one of the potential technology. So with this, like I end my talk, and there are some few interesting kind of development happen like in Finland through my research. So some videos are surfaced, so you can all download them, watch them. And also like a good news I wanted to share, this project I received the funding from the technology industries of Finland, and also it was a combined funding with the technology industry of Finland and Jane Ato's Arco Foundation. So this project is started from August, and we are progressing very well. And with that, like I thank all my colleagues like who helped me in achieving like such milestones, and I thank like all my financiers, and I thank you all, and I'm open up for the questions. Thank you so much.
Yeah, thank you very much, Professor Ashmi, for your excellent presentation on dye-sensitive solar cells.
Thank you, sir. Thank you.
Yeah, the session is open for the discussion. Dear participants, if you have any questions, please write in the chat box, or else use the option raise hand. That we will allow you to interact with the speaker.
I'm sorry I was like bit slow because like I had a tooth extraction yesterday. So, and I don't know
Okay,
how did I
okay,
manage
no,
today. So I was in
yeah,
severe
that's
pain.
not a problem. Yeah, Shukdev Pandey, are you there?
Yes, I'm here.
Yeah, you please interact with the speaker.
Hello, Dr. Gufran. Thank you very much for this enlightening presentation. I have a few questions.
Yes, sir.
Throughout the slides, I saw in most of like the results that the 10 like for the 10% and 50% exposure, like the efficiencies were greater than the 100% exposure. Can you shed some light on this? That why is it so?
Actually, like mostly, yeah, you are achieving first of all like kind of the high open circuit voltage. If you try to you make a plot, because you always like have to see with this bulky electrolyte, you have to see like the diffusion profile, because as I mentioned that there is a great problem. And what happens, so then like if there is no diffusion kind of problem with the in the solar cell, with this bulky redox shuttle, so then you get a linear trend. If you draw the with different light intensity the short circuit current density, a plot like of the short circuit current density versus the light intensity conditions, so you always get a kind of the linear trend. And what is happening in mostly like the full sunlight, so we see like some kind of diffusion problem, and that's why the linear trend like it deviates. So a lot of kind of work has been going on to optimize even the thickness of the the photoelectrodes. So what happens that and you will have noticed if you see our this recent review article. So one of the section is that this advanced titania electrodes, where I wanted to highlight this important development. So these days, with these alternative redox couple, and also like with these new dyes which are having this high absorption coefficient, so it is possible now to make very thinner electrodes to suppress this kind of diffusion effect. So that's why, like under this low light conditions, we don't see much. If you see like other published reports, so so that is one of the reason, kind of
You think, but you think that it's kind of like a blessing in disguise that if like these devices can work in low light better than high light, I mean, like kind of.
I would say it's it's a blessing, because like one of the fact you should know, even like the standardized kind of lamps are not determined yet. You know that with this kind of LEDs, and like there are variety of kind of and that's why we also mentioned the importance of highlighting the kind of the consensus, that how to report the stability of these kind of special category of the solar cells that will be deployed, and even the the stability testing protocols. As you have noticed maybe, that there is a consensus statement reported for the perovskite cells, so in Nature Energy. So now we also urged in our this article to make a census, a consensus, like for to establish,
Right.
so
Let
these
me
are all
get to
unknown.
my second question.
Yes, sir.
Yeah, thank you for your answer. So the second question is like about these equivalent circuit parameters. Can you share with us the equivalent circuit
Let me
parameters for
just
the
quickly.
carbonaceous? Yeah, sure. Yes,
Yes,
probably
sir.
this one. Yeah, for the carbonaceous solar cells. And can you like just like explain again quickly that
Yes, sure, sure.
what are we aiming for? And like, are we just aiming for like reduced like Z prime, like the real part of the impedance?
I
And
explain it. I explain it to you. Actually, like in typical, like when you do with the platinum counter electrode catalyst materials, so you always like get like mostly three impedance kind of arc
okay,
at the
three
moment,
arcs.
because yes, so this is like a, you can see only one big arc, and it is like actually merged with the kind of because the diffusion resistance and very large charge transfer resistance, it was very difficult to see, you know
To separate them out,
to
kind of. Yeah.
separate them out, right? And then, but in this kind of carbonaceous material, if you see, so this
Mm-hmm.
first one, like as I mentioned, it appear very small, like kind of semicircle,
Yeah,
that
a small.
you
Yeah.
don't see it, you don't see it, like kind
Yeah,
of
we can't see the
that
profile
comes
properly.
exactly. And then, like the charge transfer resistance for the platinum, it appears at the high frequency response, but in carbonaceous material, it appears at very low frequency response. That's why
I
it is
see.
always obligatory to make like the symmetrical cell, because mostly in this iodine kind of cells, even this
Mm-hmm.
small semicircle, people or researchers are claiming that this is a charge transfer resistance. No, it's not. It's the input diffusion resistance. And then like another semicircle like appear, for example, here you can see there is no photoelectrode like made, so there should be no third response, right, of the
Right.
third semicircle. But here you are
Mm-hmm.
still watching like all observing three semicircles. So why is
Mm-hmm.
that? It's because that, okay, the carbon counter electrode exhibits these three. And then this diffusion resistance, as I showed you, that by just changing the inter-electrode distance, like with the thermoplastic from 10 micrometer to kind of 25 micron, so you can see a large diffusion resistance was induced. So with this
I
kind of
see.
electrochemical characterization, you can like you can see how to minimize it. And that is affecting like the not only the open circuit voltage also, but also like the fill factor of
Right.
the LED.
I see. Okay, so my last question, if you have time, the last question is about the reliable process control slide that you showed. There were like these two graphs, like a red and blue, and the red was higher than the blue. And as far as I remember, the red one was after 3 weeks. So can you explain me that why is the
Sorry, let me
performance?
just quickly
Yeah,
go back
sure, sure.
to where was it? Where was it?
It was in the end, last slides, probably in the
I
last slides,
think
actually, in
this
the
one,
end.
yeah.
No, it was actually in the end, like maybe the third last or the fourth last. The
Oh, yeah, the reliable process
the
control,
reliable
right?
process control, yes.
This one, yeah. This one?
So there was like a graph which you were sharing with the results. Maybe there were a few comparative graphs with a red and a blue.
Yeah, this one. Yeah,
This
this
one,
one.
yes, this
Yeah,
one. So
yeah,
here, what I
yeah.
see is that
I
the
I show you. I describe it. For
so
example, next to this.
after 3 weeks, so
Yeah.
like the performance improves, like the
Yes.
VOC is higher, the FF is
Yes,
higher, and
absolutely,
so can you
absolutely.
explain that, please?
Yes, I can explain it. So you should read one of my article. It is called High Performance Carbon-Based Printed Perovskite Cell with Humidity Assisted Thermal Treatment. Okay. So
Okay.
there, like we found that, okay, if you, soak the devices, or if you even like encapsulate the devices,
Mm-hmm.
and then like kind of, so then as a result of, at that time, it was like
Mm-hmm.
unexpected crystal growth that was happening
Mm-hmm.
like in between the perovskite. So please, go through like that article, and then you will realize what impressive discovery like was made through finding that even like if you expose the devices under high humidity conditions, so then
Mm-hmm.
instead of performance degradation, the the devices, the photovoltaic performance like improves.
So would
So
you say that your device would be rather more ready after 3 weeks rather than buying it like after, like we need to wait for some time to like
but this is
have the
for the
better
perovskite,
performance?
like, okay, so of
Okay,
course
yeah.
you are absolutely correct. So yes,
Hmm.
even
Interesting.
I have now even like proved that even with the large modules, you must have to soak the kind of the solar
Hmm.
cells or panels into the humidity chamber. And now we
Hmm.
are optimizing like that time, that okay, how can we achieve, let's say, in 24 hours, for example,
Hmm.
like kind of like at the moment it takes like 3 to 4 days, 100 to 200 hours, because like we are soaking them under mild conditions. But now we are trying to optimize that in order to achieve the similar result like in a short period of time. So
Very
that's
interesting results. Thank you so much for your explanation.
thank you,
Thank you,
thank you.
doctor.
So any other question?
Sir, I have one question.
Yes, sir.
First, I thank you for your nice and excellent presentations, and the
Thank you, sir.
organizer for organizing such a wonderful talk.
Thank you, sir.
So, since you have used a copper-based electrolyte, what about the corrosion analysis of your solar cell?
Yes, very interesting question. So you know that, okay, one of the research ambitions for this technology is to replace like one of the electrodes, let's say, these glass electrodes with the low cost metals, right? Like for example, stainless steel. But like the problem with this iodine or iodide triodide redox couple was that these redox couples are like very corrosive in nature, and then they corrode like in seconds sometimes. Okay, so you are absolutely correct that the metal corrosion is studies, or like kind of the corrosive nature of this copper redox shuttles is not yet researched. So I am also like moving towards this direction. So it's very interesting question. And yes, like so but as you can see that these have these are developed very recently. So I mean it will take some time, like for this some more like kind of passionate researcher to rethink about like testing this novel shuttles, like with all the possibilities. So I would say like the time will determine.
Thank you.
Thank you.
Professor Gufran, there is two questions in the chat box. I will read out.
Yes, please.
Was there improvement in stability for using copper electrolytes with carbon nanotubes counter electrode?
At the low light conditions, like there is no degradation, like I observed, because like I couldn't publish that stability results. But now as I have moved to this new place, so we are systematically kind of planning to investigate like the systematic like kind of stressful condition. But I assure that, okay, with this carbon counter electrodes, and then like even like with this di Y123, So there is no kind of degradation occurs, or like any performance deviation occurs like under this kind of room temperature conditions. But like kind of, we need to see some more kind of, results. So soon, like you will be seeing like, some studies coming up, uh, not only from my group, but
Okay.
also.
Yeah, that's fine. Thank you. And another question is from same Azina Shakriya. She asked the next question is, which dyes you have used for carbon nanotube counter electrode based dye sensor solar cells?
So it is like called this dye Y123. So you can see all the details like in the kind of, the heading of that article I've shared in one of the slides. So here I think I mentioned, yes, dye Y123. It was from Dynamo, but you now you will also have to co-sensitize it with another dye, let's say XY1, it is coded. So that is also like working very efficiently with this alternative redox electrolytes.
Thank you, Rashmi. And another question is from Adilakshmi. She
Sure.
madam asked, sir, how to printed on textile or papers? Is there any special machine?
For paper is very easy, but for textile like is sometimes challenging, because how to kind of, handle, let's say, a piece of cloth on the printing. So mostly like this kind of textile printers or like the digital printers, in my opinion. Now you can see recently, now there are like even the t-shirt kind of printers appeared. So I am believing that there would be some solutions available in near future. Like, you just can like put that kind of t-shirt, and then all these active materials can be intelligently printed. So I don't know if you have seen that video, even from like some very famous producers. So they are now printing these kind of t-shirts with a digital printer. So I believe that, okay, that is the way you can deposit the material.
Yeah, that's fine. Thank you, Rashmi. And participants, if you have any questions, please type in the chat box, or else use the option raise hand. We will allow you to interact with the speaker. If you have any questions, please type in the chat box. Or else, if you want to discuss with the Professor Rashmi, he is available. You please use the option raise hand. You can interact with him.
Okay.
Professor Rashmi, could you please type your email ID in the chat box so
Okay,
that
sure.
participants
Yes,
can
absolutely.
yeah,
Absolutely. I can
can
type
be
it
able
here.
to reach you. Yeah.
So here is my email address. Okay, I need to excuse because I can't bear anymore the toothache of my, so I have to leave.
Okay, okay, okay,
But
that's fine.
I
That's
hope
fine.
that I mean the message is kind of delivered. So
Yeah,
I'm
yes, yes.
I'm very sorry.
Yeah, okay, no problem, Ashwin. And on behalf of our college, thank you so much for delivering this talk, even though it is an early morning, rushing out to reach your office. Thank you so much, Ashwin.
No worries.
We'll see you
Thank you
soon
so
in our
much.
campus.
Thank you so much,
Thank
like
you so much,
everyone.
Ashwin.
Thank you so much. Thank you so much.
Yeah, thank you
Bye
so
bye.
much.
Bye.
Yeah, bye. And instruction to the participant, the next session will be start at 1:30 p.m. Please try to join the same link around 1:15 p.m. That we will be having one special speaker from Italy. He is the eminent professor in the field of nanoscience and technology, especially on silicon photonics. Those who are working in the field of solar cells and on kind of energy conservation field, you have a very good opportunity to interact with him. He is such an eminent professor who is having highly cited, most highly cited European. Okay, please try to join as early as possible. Thank you so much. You can fill the feedback form which is available in the chat box. The same meeting will be broadcasted in the YouTube. Please try to join the meeting within the time. After that, if the maximum number has been reached, you are please requested to watch the same broadcast in our college YouTube channel. You can just put Chettinad College of Engineering Technology in the YouTube. There you can find out our college website, college channel. There you can have live broadcast. Thank you very much, participants.